All right. So, on our things today, right? You're so excited. I know. I'm excited too. We're going to do lots more problems. Yay! And don't forget, we're doing review for the test on Friday. So if you have a specific question you want me to definitely cover on Friday, email me and say, I for sure want you to cover this. If you're embarrassed to raise your hand and just do it in class, that's fine. You can certainly raise your hand in class and just do it. But if you want me to definitely cover it, send me an email and I'll do this first. So, what we're going to do is I have just a bunch more practice problems for us to just kind of work through and read. Yeah, Lily. Yeah, here's my debate about having a group quiz on Friday. Like, one, it'd be great review, but on the other hand, you wouldn't get it back before the test. So I probably will not have a group quiz on Friday. So, yeah, I know. But if you want to come take one anyway, a freebie, come by my office and we'll work something out. Oh, let's see. Practice problems or review on Friday. If you have specific questions, email me. And we will not have a group quiz on Friday, so that you can spend that time studying. Yeah. All right. All right. Let's say I have yes, A100 and 100 and 100 100 milliliters. However that grammatically works out, because right, 100 is an H, that's tricky. And 100, A100, 100. Whatever it is, that's how much we have. You have 100 milliliters of sample of 0.2 molar HF, and we're going to titrate that with 0.1 molar KOH. I want to find the pH of just these 2 points. One, before I started, and after I've added 100 milliliters of potassium hydroxide. Alright, so what is going on in this solution? What kind of titration is this? Alright, HF is strong acid, weak acid, strong base, weak base. Ooh. It is a weak acid. It is a weak acid. This is a tricky one. Like a lot of the other H halogens are strong acids, HF is the exception. It is not. It is a weak acid. Alright, so this is a weak acid titrated with what is KOH? Definitely a strong base. So I have a weak acid, strong base. So, make note of that. Alright, so there's a strong base, weak acid titration. Yes, I will give you a Ka, certainly. Do you want the Ka of HF or a Ka of KOH? Right, why can you not have a Ka of KOH? It's a base! Trick question. Yes, you can't have a Ka of a base because A stands for acid. Alright, so Ka is what? 3.5 times 10 to the negative fourth. Alright, so before the titration starts, what are my two reactants? Okay, HF is one of them. What's the other reactant? Water. Yep. Alright, so then, before the titration starts? No. That's a strong base. Yeah, so before the titration starts, it's just HF floating around in water, hanging out in a speaker, enjoying life. I imagine HF like on one of those little rubber ducky inflatable tubes, just like floating around, waiting to react. No? That's what I imagine is going on in the speaker. It's relaxing. Titration, chaotic. It's like a typhoon. There's like all this extra water's coming in, reactions are happening, splashing. No? To me, this is why chemistry is fascinating, because I imagine what must be going on in there. Apparently, I'm alone in that. That's fine. All right. So then, what should be my what should be the product? What am I gonna make? F minus and hydronium. All right. Before the titration starts, have I added anything? No. So what kind of ice chart should I make? Just a plain ice chart. So what unit should I be in? Molarity. Okay. Just a plain ice chart because nothing has happened yet. Alright, and they gave us molarity of this. Alright, and that's water. Do I have initially either one of my products? No. Okay, so those are zeros. So what do I put in the change column for the HF? Minus X. What do I do about my two products? Okay. Alright, now what? Set it up. How do I set it up? What equals what? Alright, now I know the Ka, so that's 3.5 times 10 to the negative fourth. What can I do to prevent a quadratic from occurring? Assume X is small. Alright, let's see here. Am I done? Yeah, so I haven't actually finished solving the problem, right? So wants the pH. So based on where I'm at right here, what do I do next? Negative log, right? Because X in this particular case is the hydronium, which is pH. So we can just go ahead and say pH is negative log. That's I remember to double check my work. All right, let's see, 3. I didn't look at my notes before I came to class today, so I apologize. Okay, 3.5 times 10 to the negative 4 times 0.2. So you're getting 7 to the negative 5th? No. Okay. Negative third. Oh, as x. Yeah, I did. Little issue counting across my zeros. That's what I do. Like, there's like little tiny pen marks on my calculator because I'm always counting as I go across. I probably should just put into scientific notation on my calculator, but that would be like extra button pressing. And alright, so now that I've solved my issue, well, this one particular issue, does that pH make sense with what we know is going on in the beaker? Because we have a lot of it. Yeah, there's a lot of that weak acid, but at least it's on the right side of 7, right? Ballpark, we're doing good. Alright, so then part B, I now want to see what happens when I add 100 milliliters of potassium hydroxide. What are the key words in that part of the question? Added, so now what? Yes, and what units? Moles. Okay. Alright, so what are my 2 reactants now to set up my IACE chart? HF is one of the reactants still. What's now my other reactant? The OH minus. I mean, sure, you could say plus K plus, and then you end up with, yeah, H2O and an F minus and a K plus. Then, yeah. I mean, you can certainly write them if it helps you keep track of them, and then get rid of them. I find it confusing myself to do that. So, alright, so we have to be in IACE chart, so I need to be in moles. So how do I find, I guess I'll do it down here. Moles of HF, what information do I have to find moles of HF? I know the molarity and I know the liters, right? Well, in this one particular case. But it's a good habit. It's good. So many moles of HF. Good. My notes are wrong at this point, so I made a critical math error. So at this point, I'm winging it. So definitely double check what I'm doing. I apparently was reading 2 different questions when I did my practice set. So, all right. So now we can plug some things in, right? We have this 0.02. None of that. This. All right. So what's the only thing I've added? OH minus, right? So let's go ahead and plug that in. Of my 2 reactants, what is the limiting one? The OH, right? So I subtract that from both reactants and add it to the product. All right. What do I now have? I do. I have a buffer, so we can use the Henderson-Hasselbalch equation to test it. Well, yes, right? So I'm going to set up I'm going to show you everything, but you recognize at this point that they're equal molarity, so it's going to equal the pKa. But if you don't see that, then this is how that works out, right? So I recognize that I have a conjugate acid-base combination. Do I need to convert this to molarity to use the Henderson-Hasselbalch equation? I do not. I can leave them as is. Okay? Yes. Yep, if you want to convert to molarity, which is fine, it would be in 200 milliliters. Yep. You do not have to. The Henderson-Hasselbalch equation, because it's base over acid and they're in the same volume, the liters end up canceling out. So your option, you can do it in moles or molarity, whatever is easier for you. Alright, so I know what B over A is. How do I find the pKa? So you can see at this point, we happen to be at the point where these two are equal in moles to each other, so this becomes 0. Right? So the pH equals pKa. What do I call that point? The equivalence point. We happen to be at the equivalence point, which you can see that now. So if like part C was, what point are you at in the titration? You're at the equivalence point. Yeah, sorry. Yeah, you're going to have to double check all my work today. At the midpoint? There's a third one. Hold on, let me think. No, this is the midpoint. This is the midpoint. Alright, so the midpoint is where we're at now. My fault. It's a chaotic day. The midpoint is where the pH is pKa. The equivalence point is where the base added equals the acid to begin with, and then you do the double ice chart. Right, that's a really long problem where you end up with zeros as the reactants, but you have a lot of product. And then you go on and do a second ice chart. We'll do one of those here in a little bit. Yeah. Probably not. It's such a long problem to solve, but I know it's on the mastering. So at least do it. Yeah. Alright, so the answer, part B of this question, the pH. Does that pH make sense with what has happened to your solution? Yes, it became more basic, right, when we added base. So good. Alright. Alright, let's do... let's see what problem I can come up with. Alright, let's try this one. so let's do the most complicated one out there. So you're going to titrate a 30 ml sample of 0.25 molar, what's this guy? Acetic acid with 0.1 molar sodium hydroxide. Let's look at the pH before, at the equivalence point, and at the midpoint. What information do you need that I haven't given you yet? Ka of the acetic acid, which is alright, so what's happening in my beaker before titration starts? Who's in there? Who's a reactant? Acetic acid and water, right? Which will then make the acetate ion and some hydronium. Alright, before the titration starts, what sort of chart should I use? Plain ice chart, right? So if I'm in a plain ice chart, what sort of unit? Just regular molarity. So 0.25. How would you show me, if I asked for it, that the X is small? What rule would you have to use? 5% rule. Okay. Alright, so let's see what this X is. Alright, then what? Negative log, right? Say reasonable pH. Yeah, right, less than 7. Alright, questions on that part? In that case, let's do the equivalent point. That's the trickiest, right? Leave yourself lots of space. Yeah, so 5% would be 2.12 times 10 to the negative third divided by 0.250 times 100%. What is that? I think we're in the clear. 0.8%. I think we're good. Alright, so now the equivalent point. The equivalence point is where the moles of the base added is equal to the moles of acid that were sitting in there. Which one can we find first? Right, we know all the information to find the moles of acetic acid, then we'll have to figure out how many moles of base that was. Alright, so in our original problem, we had 30 mils of 0.250 molar. Alright, so if I know I have 0.075 moles of acetic acid, what can I now set up to fill in? The IACE chart, right? So what are my two reactants now? Oh. Yep. What did I get for coming up with a problem off the top of my head? Okay. 2 zeros. Yep. So I'm going to have CH3COOH and the hydroxide. How would you double check to make sure that that's the right thing? What are the two main ways you can check to make sure you did it right? Is it mass balanced? Right, so mass balance means I have the same number of carbons on both sides, I have the same number of oxygen, right? So that's the first thing you should double check if you're not sure. Second thing is charge. Make sure that both sides of the arrows have the same kind of charge. So on this side, I have a -1, and on this side, I have a -1. That's two good things to check. If you're not sure you picked the right products, those are two easy things to kind of double check your work. Plus, you'll always have water as one of the options. Of the 4 slots, water will always be in one of them. So make sure water is always in there. If you end up with hydroxides and hydroniums in the same equation, you've done something wrong. And you can have hydroxides in water or hydroniums in water, but you can't have hydroxides and hydroniums. That's a good tip. Alright, so initially we have this. I haven't calculated anything about sodium hydroxide, but what do I know the moles added have to be? Right, it's the same number of moles of the acetic acid. Oh, I guess that should be zeros for this. Alright, so here's this point where I'm out of reactants and I have all products. Why do I have to do a second ice chart? Right, I have nothing to take the pH of. Right, there's no hydronium in here at all, and there's no hydroxides left. So I have to do a second ice chart to get to the point I can find my pH. Plus, what does Le Chatelier tell you if I have all products? Have to head back to reactants, which, good review question, that'll be on there. Alright, so now what should my reactants be? The acetate and what else? Yep. Alright, in my second ice chart, am I adding anything new to the solution? No, so what kind of ice chart do I need? A plain ice chart. What units do I need to be in? Am I in molarity yet? No, right? So this ice chart has to be a plain, boring ice chart, which has to be in molarity. And the only thing I know about this acetate ion is its moles. So before I can start my second ice chart, I have to figure out the volume that I used and then the molarity. You could have done this ahead of time. I tend to do it at this point. Whatever works better for you. Alright, so the question is, I know I started off with 30 milliliters of acetic acid, but I added hydroxide. So I need to figure out how many milliliters of hydroxide I added to find my new volume. Right, so that's the question you're asking. I know I had 30 milliliters, but I definitely added hydroxide. So I need to figure out how many milliliters of hydroxide I added before I can do the second ice chart. How could I possibly figure out how many liters I added? What do I know about the hydroxide? I have the molarity and the moles that I needed, right? So I guess side note down here, or maybe I'll do it on a separate sheet. Right, so we knew we used that many moles, and I know moles per liter, so I can find liters. So how many liters total must I have used? Yep, so I had 30 milliliters, which is the same as saying total 0.030 liters plus my new amount. How do I know to do it this way? The only way those moles cancel out. Right, because I want to end up in liters, so those liters have to be on top. Otherwise, you end up in like inverse liters, which is, I mean, ridiculous would be a good word for it, yeah. Alright, so now I know how much my total volume is. Going back to this chart, how do I figure out what my molarity is now? Take the moles and divide by my new volume. Alright, so now we're ready. Now we're ready to do the next chart. Just a little bit of prep work to get ready. Just a little bit. Alright, now we're ready. Alright, this is just a plain old ice chart. We got this. Alright, so now what? I need the KB. Why do I need the KB? Because now I have the base. What if I felt like I was being tricky and didn't give you the KB, but you know the KA? So you could either say KW equals KA times KB, totally fine. Or you could do a few other circuitous routes, or I'll be generous and I'll just tell you. In this case, and again, I'm going to assume X is small. I think that'll be a reasonable assumption. Is that numerically small compared to 0.07? Yes. So you certainly could do the 5% rule, but eyeballing it, it's going to pass. So now what? If I take the negative log of this number, what do I end up with? POH, totally fine. I think that's the easiest thing to do, but just remember that this x is this guy. Are you done? One last thing. I want the pH. So how do I get the pH from the pOH? 14 minus that. How fun was that? It only took like 2 pages of paper. And we didn't even do it like the trickiest way. I didn't account for a whole bunch of other factors. Maybe one 100-point question is just that. Oh, okay. I'll think about it. Probably not, to be honest. I'll probably pick something else. Only because we cover every chapter. All right. Midpoint. Yep. Hopefully you left space for this. Which, did we calculate the pKa yet? No. Does that midpoint pH make sense with the trend that you saw? Alright, so our original pH was 2.7. Our equivalence point was, what did I just solve? 8.6 something. Halfway between those two, does that make sense? 4-ish. That's the way I asked the question. Yeah, so the midpoint pH is equal to the pKa of whatever the acid is that's in the flask. It's rubber ducky, inflatable tube, hanging out, being titrated. Yeah. Cool. Yes. Always. That's how it's defined. The midpoint is where the pH equals pKa. If it's a strong reaction, then you can't have a midpoint. Yeah. So it has to be a weak, strong combination. Right, because this is really coming from the fact that pH equals pKa plus log base over acid. And at the midpoint, that's equal to 0. There we go. Oh, that's right, you can do your first question first. No. Yeah, I have to give you the Ka. We didn't have to. But I didn't tell you were at the midpoint. Like in the previous question, I did not say you were at the midpoint. You didn't know you were there. In this case, I specifically told you you're at the midpoint. So you can just jump to the conclusion of that. Unless you're really fast at math in your head. They're in the appendix. They're in the appendix. Well, that's right. I think what I'm going to do is I'm going to use a different online homework system next year anyway. I think I'm going. No, you're already locked in this semester. Yeah, there may be some way I can change the question. I just have to look to see how I can edit a question. Yeah, I need to figure out what's the easiest, because some of them I can comment on them, and some of them I can actually change the text. I just don't know. Yeah. If I'm feeling generous. Alright, are you guys mentally done, or you want to do one more? Done? Alright. I could do these all day, so. If you're feeling tapped out, we'll just do more on Friday. Alright. Go team, chemistry. Woo! Woo! Hold on.